To continue from the last segment, let's still looking looking for appropriate atomic units. Well, let's take those primary constants that play a central role in atomic systems, and that's the mass of the electron, the fundamental charge on the electron, the magnitude of the charge of the electron, and Planck's constant rationalized divided by 2 pi, so h bar. In addition, uh, we'll also take the simplifying factor that we'll use the CGS Gaussian for the potential energy term for these hydrogen and hydrogenic type atoms. And with that, we can obtain a more appropriate system of units for things on this atomic scale, and they're naturally enough called atomic units. They were, I don't know if they were invented, but they were certainly popularized by Douglas Hartree, who was an early day physical chemist who did lots of computer calculations on the atomic scale. So let's look at there's a way to find these by looking at things in maybe a little bit different way. I want to obtain a more appropriate a set of units, and to find this set of units, what I want to do is I want to be able to find a fundamental length, a fundamental energy, and a fundamental momentum, and there may be other quantities as well, but certainly these first two are primary for us. Uh, we already have a fundamental charge, that's the charge on the electron, so I should probably just introduce call charges however many electron charges there are. Also mass, we've got a fundamental mass of the electron. So I'd like to find what would be appropriate lengths, appropriate energies in particular, and I'll deal with this other one, fundamental unit for momentum, linear momentum. And by that I mean, well, I want to have some defined length, which I'm going to denote as A naught at this stage for historical purposes, in which I'll report things in terms of this fundamental length. Now, fundamental length on our scale is meters, maybe, or centimeters, as the case may be. But on atomic scale, we probably would expect this to be much, much smaller because atoms are fundamentally much smaller quantities. Also, energies, energy scale, which for historical purposes, I'm going to call that E sub h. And then momentum, we won't deal much with that except as an auxiliary, but a fundamental unit to measure momentum in. We've already done some of this in that, for instance, energy. Sometimes it's appropriate to measure things in joules, and then you get in atomic physics start getting things like um, 10 to the minus 18th in a value. And so you introduce electron volts to bring that down into maybe a 10 or 5 electron volts just to make the numbers easier to talk about. Okay? So we'll want to look at those and construct some of these. Okay? And we want to be able to build these fundamentals up from the primary characteristics, the constants that really characterize the atomic scale. And that for us is m, the mass of the electron, the charge on the electron, and then Planck's constant. Well, remember how Planck's constant, one way it arises, is in the quantization of angular momentum. It's just an integer times this for orbital angular momentum. And angular momentum, if you go back and look at for a particle, it's just the r times p. And what I want to do is I want to be really just thinking in terms of a fundamental unit for length. Well, I've already got one of those. I introduced that as A naught. And a fundamental unit for momentum, P naught. Now, I don't know what they are right now, but I know that I'd like those to be related to this fundamental, through this fundamental equation, this constant h bar. That gives me equation 1. I can also look at other terms like kinetic energy. I know that in general, kinetic energy of a particle is its momentum squared divided by 2m. And so the 2 is irrelevant. It doesn't have any units. And so if I'm just looking at a unit involved with this, I would say, well, it's the units of momentum squared divided by the typical mass, which is, again, is our chosen mass, me, that we'll express things in. And then likewise for potential energy. Potential energy, remember, for these systems looks like this. We're using the CGS Gaussian units. And I get that whatever the units are over here, it has to be in EH. That's our fundamental unit of energy. And the Z is just an integer. We don't care about the minus sign, so I get an E squared on top. And then the fundamental unit of distance is just this A naught that we introduced earlier. Well, I can solve equation 1 up here for P naught. That's just H bar over A naught. And then plug that into equation 2. So if I do that, I get H bar squared over A naught. And as a result, I get H bar squared, simplified a little bit, ME A naught. So I've got two fundamental constants. This one I still need to determine what that is, but I'll call that equation 4. And then from equation 4, if I look at equation 4, I've got the fundamental unit of energy is this, and it also has to have this expression. So I set those two equal. They're both equal to EH. And then I can solve for A naught. So I get an equation here that is the one side over the other side. Both of these are EH. And we find that when I solve this for A naught, I get H bar squared ME over E squared. And if you plug all these values for all of these quantities in, or you may recognize the formula, that is simply 0.529 times 10 to the minus 10th meters, or about a half an angstrom. And if you recognize that, this expression is just the Bohr radius. So an appropriate unit might be that value in terms of our meters. Rather than use that, rather than using meters, use this to however many times a length is of this Bohr radius. We can use that expression in 3. So here's 3, I get EH, and I've now found A naught in terms of our fundamental quantities. It was just this, so plug that into equation 3. Here it is. Plug it in here, and then simplify. And if you may recognize that expression, but now I only have those fundamental quantities: m mass of the electron, it's the charge, and Planck's constant over 2 pi. And this E naught is EH here. E naught is EH, and that is usually represented EH. It's named after Doug Hartree. And it's called one Hartree of energy is this amount of energy. It has units of energy. If you remember maybe from laboratories or other areas, you may have used Hartrees already, or you may have used what's called a Rydberg. The Hartree is actually 2 times a Rydberg, and a Rydberg of energy, remember, is 13.6 electron volts, and so Hartree is 2 Rydbergs. And a Hartree is, if you put in the standard values for all these constants, you get, and then turn it to electron volts, then you get that 1 Hartree is essentially 27.2 electron volts in more traditional terminology. So What we do is we express energies in Hartrees, and the conversion factors are these. We express lengths, maybe x or y, lengths, distance measurements, in what's called a Bohr, and that's this unit of length in terms of. So 1 Bohr is equal to half an angstrom, and 1 Hartree of energy is 27.2 electron volts. And now then, if you take a look at all of these, what I've done is I'm defining a charge in terms of it's a number times the fundamental charge on the electron, and this number in atomic systems is always going to be reasonably sized, 1, 2, 3, etc. Or it could be -1, -2, -3. Likewise for masses. So long as I'm only dealing with electrons and about a nucleus, then I can express masses as a number here times the mass on an electron. Uh, Likewise with any distance here, I used x, but I could have used y or z or r, a length, any length. I express that in times a naught. Notice I chose the a naught appropriately because that's the Bohr radius symbol. But the number of Bohr radii, don't express it in terms of centimeters or meters. Those are much too large a measurement scale. Instead, use the number of Bohrs. So, likewise for the energy, I have expressed them in terms of Hartrees. H, the symbol. And likewise for momentum, express it in terms of a number times a Planck's constant divided by 2 pi. And in all of these, the QA, the numerical part, are all of appropriate size. Now you'll see a lot of people that will say, well, to express these things, we're setting mass of the electron equal to 1, I guess, and the Bohr radius equal to 1, or the Hartree energy, or h bar equal to 1. That's a common expression. But really what you're doing is you're setting the scale by those factors.